Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, Tifr, Jest, IIT-Jam and other exams related to physical science. Okay. So guys, this is the lecture number 7th of optics, in which I'm going to solve just PYQs, just optics PYQs, and and also I would like to request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures, which are going to help you to crack the exams related to physical science. Okay, so guys, I'm going to start now with just PYQs. The question number first is, okay, question number first is, just let me check guys, let me, yes, okay, the approximated force approximated the approximated force the approximated force exerted on a perfectly reflecting mirror by by an incident laser beam of power 10 milliwatt at normal incidence normal incidence is, okay. Options are: option A 10 to the power minus 13 Newton, option B 10 to the power minus 11 Newton, option C 10 to the power minus 9 Newton, and option D is 10 to the power minus 15 Newton. Okay, this type of question I have already explained in optics gate PYQ guys. So okay, so this is a just question which is asked in just 2015. Okay, so this is the question: the approximated force exerted on a perfectly reflecting mirror. So we are talking about perfectly reflecting mirror. Okay, by an incident laser beam of power, this is given. Okay, so we have a formula guys: force exerted, the approximated force exerted on perfectly reflecting mirror by the incident laser beam of power 10 megawatt for any this we have a formula for force exerted uh, by the beam, laser beam. Okay, a beam of laser. Okay, this we know, that is 2p upon c. Okay guys, this is the this f is 2p upon c, or in case of perfectly absorbing mirror, right, or in that case it is going to be or for object, okay, which is perfectly absorbing object, the force exerted is going to be P upon C. It is these are formula for normal incidence of light, okay, P upon C. This for perfectly reflecting object, perfectly reflecting object, and this is for perfectly absorbing, okay, absorbing object, okay, very important formula, okay, so you can note down. For perfectly reflecting object, F is force exerted by beam is 2P upon C, and for perfectly this is perfectly reflecting object, okay, and this is for perfectly absorbing object, the force exerted by beam of light or beam of laser is P by C, okay, this you need to note down. So here we can easily solve it. So this is F equal to 2P upon C, right, or P is given, since P is given, we have been given P, okay, that is power, okay, 10 milliwatt, or we can write 10 into 10 to the power minus 3 watt, okay. So this is the one. This is a force, okay, 2P upon this, 2P, P is a power, guys, okay. So F is going to be 2 into 10 into 10 to the power minus 3 upon C is 3 into 10 to the power 8, right. So this is going to be, if we solve it, 6.6 into 10 to the power minus 11 Newton. So which option is matching, guys? Here you can see 10 to the power 11. So option B is the correct, approximated, okay, approximated force. This is the answer. I hope you have understood it. Next question, guys. These are just questions I'm solving. Next question is, question 2. Before that, let me just check whether I'm audible or not. Friends who haven't subscribed my channel. Yes, I'm audible, so I'll proceed further. Okay, guys. Next is this is important question, guys. This is also asking. This is also just question. Okay. The question is the wavelength. The wavelength of red helium neon helium neon laser in air laser in air is 6328 angstrom. Okay, what happens to its frequency, to its frequency, what happens to its frequency in glass that has refractive index of 1.50. So the wavelength of red helium neon laser in air is this. Okay, what happens to its frequency in glass that has refractive index 1.50? Okay, and options are number A, increases by a factor of 3, increases by a factor of 3. Option B is increases, that is decreases by a factor of 1.5. Option C is remains the same, and option D is decreases by a factor of 0.5. Decreases by a factor of 0.5. Okay, so this is the question. The wavelength of red helium neon laser in air is this. Okay, 6328 angstrom. And what happens to its frequency in glass that has refractive index of 1.50? Okay, so very good question. Okay, so now I'll tell you something. Okay, so we know here we have nu, value of nu, that is frequency. We know nu equal to C by lambda for air, for vacuum. Okay, equation number 1. And similarly, the value of nu in any medium is V upon that is velocity of that beam or light or a laser in that medium upon lambda g. Okay, for in case of glass, the velocity in glass upon the wavelength of helium neon laser in the glass. Okay, this one, question number 2. And third, we know that is mu dash equal to. Okay, and the third, that is value of v equal to velocity is C by n. Okay, n is the refractive index. So these three formula you need to note down, guys. If you know these three formula, you can easily solve this question. Okay, so this is equation 1, this is equation 2, 3, right? So now we will find it. Okay, so how? And also, guys, you need to know this is C by n. Okay, and also we know that is lambda g, that wavelength of light or beam in glass is going to be this one, lambda upon n. Okay, this also you need to note down, equation 4. So if you know this formula, you can easily find out. Okay, so this is in air. Okay, in air, this is the wavelength of beam in air. Okay, this is the wavelength of beam in the glass, or if it is any other medium, then I will write that medium. Okay, well, so I'm going to solve. Then we can write this frequency, that is mu dash. Mu dash we know that is given, right? V upon lambda g. Velocity, and velocity value we know, right? Velocity value is C by n upon, and lambda g value is lambda upon n, right? From equation 1, 2, 3, 4. Okay, lambda upon n. So from here n is going to get cancelled, and frequency nu is going to be C by lambda, and C by lambda is this one, nu equal to nu. So this implies nu dash equal to nu. It means the frequency will remain same, guys. Okay, so which option is matching? So in this case, the glass that has refractive index, this the okay. So what happens to frequency? This frequency will remain same. Okay, so these four formula you must know it, guys. Okay, so this is in vacuum, this is in any medium, this is in vacuum, and this is in any medium. Okay, this is n. Next question, guys. Okay. Next question. Next question is, so this is simple question, guys. Just question: how much force does light from a 1.8 watt laser will exert when it is totally absorbed? It is totally absorbed by an object. Okay, so simple: how much force does the light from 1.8 watt laser will exert when it is totally absorbed? Totally absorbed case, I have told you the force is this one, guys. P upon C. P is the power. Okay, so here F is going to be force exerted is and it is an exert. Okay, how much force light from 8-point laser will exert when it is totally absorbed by object. Okay, and also, guys, this is the case of normal incidence. Okay, so F is going to be P upon C. P value is given, that is 1.8 watt upon C, 3 into 10 to the power 8, right? And we'll solve it. So this is going to be 6 into 10 to the power 9 Newton. 6 into 10 to the power 9 Newton. Okay, this is the answer, guys. Okay, options are given, so this is the correct option. And here I'm going to write some formula for you, very important formula. So you know radiation pressure, I have already told you, radiation pressure is I upon C for complete reflection and normal incidence. Okay, complete absorption. Okay, and the same is P is going to be 2I upon C for complete absorption. I have already written it in explained it in gate PYQs of optics gate PYQs. Okay, complete absorption, and this is complete reflection. Okay, complete reflection. These are important formula. And also force equal to power upon C for this one. I'll write this is for this one. Radiation pressure is, this is 2P upon C in case of complete reflection, and radiation pressure, this is 2I upon C. 2I upon C. And this in complete reflection case, radiation pressure is I upon C. You need to note down. Okay. Okay, guys. So these are important formulas. So this is pressure, guys. Okay, and this is power. Understand? Okay. So So this is this, and this I upon C, this is the intensity, guys. Okay, this is intensity. Intensity means energy emitted per unit time per unit area. Okay, so you need to note down this. These are important formula, and you must know it. Okay, next question. This is also a good question. A circular, this is also just question, guys. Okay, all are just questions I'm solving. 2016 question. Circular circular fringes circular circular fringes are obtained circular fringes are obtained circular fringes are obtained with Michelson. Very important question. Okay, Michelson. Circular fringes are observed with Michelson interferometer 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 with Michelson interferometer. Okay, so circular fringes are obtained with Michelson interferometer using 600 nanometer laser light. What minimum displacement? What minimum displacement? What minimum displacement of one mirror of one mirror of one mirror? What minimum displacement of one mirror will make the central fringe the central fringe from bright to dark from bright to dark. Okay, so circular fringes are observed with Michelson interferometer using 600 nanometer laser light. What minimum displacement of mirror will make? What minimum displacement of one mirror will make the central fringes from bright to dark? Okay, that you need to find out. Options are given. Very good question. 600 nanometer. Option B is 300 nanometer. Option C is 150 nanometer, and option B is 120 nanometer. Okay, so this is the question. I'm going to solve it. Very simple question. Okay, so you need to know the condition for Michelson interferometer, and you need to note down, guys. Okay, so 2D equal to 2n plus 1. 2D equal to 2n plus 1. This is for Michelson interferometer. For Michelson interferometer, okay, 2D equal to 2n plus 1 lambda. Okay, 2D equal to 2D equal to 2n plus 1 lambda by 2. Okay, so we need to find out the value of D. Okay, so this is the circular fringes we are getting for circular fringes in Michelson interferometer using the light is given. So what minimum displacement of one mirror will make the central fringes from bright to dark? Okay, so for making bright to dark, central fringes for making bright to dark, for minima we can say, that is 2d equal to 2n plus 1 lambda by 2, 2n plus 1 lambda by 2. Okay, so this is the central fringes. Okay, 2d equal to, so 2d equal to 2n plus 1 lambda by 2. Okay, so we'll put the value. So 2d equal to, and for n equal to 0. Okay, for n equal to 0, because we are talking about central printers, n equal to 0, so 2d is going to be lambda by 2. Okay, and so d value is going to be lambda by 4, right? And we'll put the value 600 nanometer upon 4, that is 150 meter. So we have to put the put the one mirror, that is 150 meter apart, right? And then we'll get the dark fringes. Okay, so this is the answer. Very good question. So this condition you need to know. For Michelson interferometer, for minima condition is 2d equal to 2n plus 1 lambda by 2. Okay, note down it. Well, next question, guys. Okay, this is very good question. This is also, this question is just 2017. Okay, question is, a thin air film, a thin, this concept I have already explained in my lecture. Okay, a thin air film, a thin air film of thickness, thin air film of thickness d is, thin air film of thickness d is formed in a glass medium. Okay, glass medium. For normal incidence, for normal incidence, the condition for constructive interference, in the reflected beam, okay, is in terms of wavelength. Okay, in terms of wavelength lambda, and integer m equal to 0, 1, 2, so on. Okay, so this is the question, guys. A very good question. A thin air film, okay, a thin air film of thickness d is formed in a glass medium for a normal incidence. The condition for constructive interference, for bright fringes, okay, in the reflected beam. Okay, so in the reflected beam is in terms of wavelength lambda and integer m equal to 0. Okay, so so this is going to be like this. Okay, this is air. Okay, this is air, this is air, this is air, this is air. Okay, light comes here, and this is the air one, right? Air boundary, so it gets reflected, and similarly this comes here and then goes here, right? This one, this gets reflected. So this is the hard part of the glass, and this is the, so we know, I have already explained in my optics lecture, that if light gets reflected from hard part, then it creates the part difference of lambda by 2. Okay, so this is the and the thickness is given, that is d, right? So this wave travels the path of mu d, and this is going to be uh, mu d 2 mu d plus lambda by 2. This is hard part of glass. Okay, this is the air. From air boundary it gets reflected, and this is hard boundary. Okay, the gas, so it creates the path of lambda by 2, right? If any light gets reflected from hard part of the surface, it creates there is a path difference of lambda by 2, and this wave this light also travel mu d distance here, mu d distance here, so 2 mu d plus lambda by 2, there is no, right? So for constructive interference, constructive interference, path difference should be n lambda, right? So it means 2 2d plus lambda by 2, this is 0, right? Equal to m lambda. Okay, so from here you can get the condition. The condition is, options are given, guys. Okay, option is the first option. I'll write option also, then I will solve it. Okay, options are, option A is 2d equal to m minus half lambda. Option B is 2d equal to m lambda, and option C is 2d equal to m minus 1 lambda, and option D is 2d equal to m minus half d. Okay, so here for constructive interference, this is going to be this. So from here you can get 2 mu d is going to be m minus m lambda minus lambda by 2, right? So value of mu d is going to be, value of d is going to be, okay, value of 2d or value of d is going to be, 2 will go here and this one, right? So this is going to be this one, this thing, 2 mu d, mu is very small, this one. Okay, 2 will go there, so this value is going to be and you will take common, so this is going to be m lambda minus lambda by 2. Okay, so 2d is going to be here, 2d is going to be m lambda lambda will take common. Okay, m minus half. Okay, so this is the condition, and here this is given. Okay, glass medium. This is the one, guys, and here for glass medium we have been given mu is 1. Okay, that's why this value is this, mu equal to 1. So this is the condition for, so which option is matching? I hope it is visible. So which condition, which option is matching, guys? Mu is 1, guys, that's why. So option A is matching, 2d equal to m minus 1 lambda, 2d equal to m minus 1 lambda, so m lambda m minus half.